minutes, I guess we're okay. Okay, so Felipe is going to talk about the compilers, and then have some Q&A if we have time.
Hello, my name is Felipe Magno de Almeida. I work at Panda with compiler development and Linux kernel development, and own a software company in Brazil. We've worked for companies like Samsung Korea and Nevada Software, as well as many companies in Brazil. In this talk, I'll show why we need to set up a framework for hardware flows that is interoperable with different languages and software-hardware solutions, and how compilers are essential to effectively enable this. I'll propose in this presentation a new model for network offloading, and I'll propose an intermediate language that has been developed inside Panda with an MLIR dialect. I'll show how this intermediate representation allows for interoperability of several languages with implementations already in place, like P4 language and the C language for common parser representation. The first thing the user is going to do is write his parser in his preferred language, which, for example, already support P4 and C. But more are possible, as well as you see on other slides. Then he starts using the framework by compiling the parser to intermediate language, which we call the common parser representation. With this intermediate representation, we can now interoperate with backend compilers that will transform the parser in proprietary instructions for specialized hardware, or some software-generated parser in XDP or eBPF, for example. And then we'll load the program or use devlink to upload the parser program to the device. Here we see a diagram that shows the same steps as before, where the user program will be compiled by a front-end compiler to an intermediate representation, which is then later compiled again for specific hardware or software implementations. This process looks cumbersome because it requires compiling twice. However, this allows greater flexibility of user program language with any hardware, allowing the hardware vendor to focus on tools that really deliver the most value, like optimizations of the intermediate language to its hardware, and leaving actual software abstractions to open source developers to support. As I've shown previously, the common parser representation allows greater interoperability between software abstractions and actual hardware implementations, allowing each side to focus on different levels of abstractions. The Netdev community must promote a framework that hardware vendors can follow, and I think the common parser representation is the right intermediate representation, and its tools are already implemented. And MLIR has been developed to overcome standard compiler technology and its limitations. The common parser representation has been developed on top of JSON, the reasons being toolability and its declarative format. The language's declarative exceptions with the goal of facilitating its conversion for domain-specific hardware, which may not have the same abilities as general-purpose CPUs do, which leads to its definition being based on network parser concepts and a graph structure, which easily allows finding encapsulation points with back edges on the graph. And the common parser representation has native support for tag length values and other types of variable length fields. It's especially important as IPv6 and its extension headers become more ubiquitous and its complexity can't be underestimated. We will also introduce the MLIR dialects in the next slides. The MLIR is a different representation that is derived from the common parser representation, and is more appropriate for the backend compilers to represent transformations of the IR at each step. This may be reused by other hardware-specific compilers, but it's optional. What is MLIR? So MLIR is a hybrid intermediate representation. And what does that mean? It means that the intermediate representation can have multiple abstraction levels embedded at the same time. It developed as a different dialects. These dialects allow to represent information that would get lost if compiled to lower-level intermediate representations, such as LLVM-IR, for example. Also, by allowing multiple levels at the same time, the process of lowering the intermediate representation to hardware representation can be done in several passes, each one focusing on a different interpretation, pattern matching, and optimizations. With this in mind, Satana has created an MLIR dialect for passes, where it's used in its backend compiler. This is a snippet of the MLIR, and as we can see, the first part does a length check for passing at the net headers. It's checking that it can actually access the offset that it needs to determine the next protocol. Then, if it passes, it loads from the packet buffer the right offset, and then it selects the next parser node based on the value. As you can see, this is at the same time a very high-level language with structured programming, and at the same time flexible enough to be generated from any existing programming language. Also, by being a static single assignment form, SSA, it's easier to pattern match. Well, this is the point where hardware vendors can stop watching the presentation, but if you're curious, I invite you to continue watching. The point of creating an intermediate representation is to allow hardware vendors to focus on differentiating themselves and focus on hardware-related problems, like how to best utilize its strength from a common and well-known parser representation. In this slide, however, we focus on the front-end compiler and how it interprets code and generates the intermediate representation. This is an essential part of the process because it allows the user to use the language he is more comfortable with, without requiring any intervention from the hardware vendor. The hardware vendor doesn't have to support a specific language. It's done by the framework. In this slide, we show how the set-element from the front-end compiler pattern matches the IPv4 length function, and extracts the information it needs to know to determine the size of the IPv4 header. As you can see, firstly, the final value has to be the return value for the function, obviously. So we can work upwards to see how this expression is actually built. We can see that the value is zero extended, as we can see in the diagram expressing the dependency graph. It also has a constant mask which does a bitwise end operation with n shift 2 bits to the left, the value from the first byte in the header. By the way, there is some very interesting and unintuitive compiler magic here. And this is how the front-end compiler can generate the parser intermediate language as shown before by knowing which operations are done to calculate the IPv4 header. In here, we have a fork of the B4C compiler, which generates the common parser representation, which is based on JSON. So the compiler is able to know the minimal size of the header because of how much data was extracted from the packets. And it knows by the transition select statement how it must read the next protocol to match with the protocol table. So this is generating declarative form in common parcel representation, which can be used later to generate eBPF or hardware-specific offload problems. So thank you all. And is there any questions?
Thanks, Felipe.
Hi.
I think that's it. Any quick questions or? So yeah, if you have any, if you want to do any more discussion on this, I'll be around and can certainly have a breakout session. I think it might be interesting to talk about some of these issues, including the Dev APIs. Oh, there's Felipe. Any questions? All right. Great. Thank you.
Thank you.